All right, I think we were on lesson 2A, and I've got page 15. Let's start there. So we're talking about independent and dependent, and let's see where I gave you the heads up on how that works. I'm not seeing it. I'll just write it over again then. Are we on page 15 or did we get farther than that? That's where I have us. Probably wouldn't hurt to start there anyway. 16. Let's just start on 15. And so, in your notes, since we're talking about independent and dependent, when you see the function, it will be dependent outside and then the independent on the inside of parentheses. So this would be the f and this would be of x. In the equation, you would have, like in number 2, you would have dependent is a function of independent equals, and then there will be some coefficient times the independent variable, and it might be to the second power or the third power or something, but all of the stuff on this side of the equation is only going to have the independent variable. So in number 2, as an example, here is the here is the function for number 2. So you notice I've got the equation here, negative 4.9t squared plus 20t. And then you can see that the independent variable is along the horizontal axis, and then the dependent variable depends on it, right? And it's going in a curve because it's to the second power, right? To the second power there. And all this is saying is that gravity pulls it down at twice this, so that'd be 9.8. But the guy threw the ball up at 20 meters per second. Number 2A then, the two different quantities are involved, time and height. The dependent, what did you have for A? Height. And then the independent, time. Just like David Bowie said, right? Time, you can't change time. Page 16. This is where we were, someplace along here. So if you notice here in the graph, I just made the time different things here. So I'm going to graph time. So let's say x equals a. So if you notice here, as I go along, I'm graphing vertically, and then it's pretty easy to do. All you do is you substitute into the equation and you get your answers. Okay, so number 1b on the top of the next page says, if you were asked to compute the height at 3 different times, what did we say would be the way to do it? Just plug them into the equation, right? C, if you were asked to go the other way around, notice you have to change things up here. Now we're going to do our y's. Why can't this play? Y equals try adding. No. Let's do it this way. Y equals H parentheses A. There we go. So now we're going the other way around, and we are graphing the horizontal, right? The independent or the dependent variable. Well, if you just given the independent variable, you need to go across till you get to the graph and then read down. Okay? Are there other ways that you could solve this one besides that? So in other words, we want to have, for letter B, just plug into the equation. So if you had h of 3 seconds, you would just take negative 4.9 times 3 squared plus 20 times 3. Got it? But for letter C, you can't do that because it's not solved for h. So the first thing you would have to look at is you would have to say h of t equals negative 4.9 t squared plus 20t. You have to get the t all alone, which would be easy if it only appeared once in the equation. But it doesn't appear once in the equation, it appears twice. Right now, at this time, I have not taught you how to find that, all right? There are some people that may know how to find that using the quadratic formula and solve it for x and figure out what that is, given a certain value for y. But right now, we haven't done that yet. How do you find the y value, the x value if you're given the y value? The way to do it right now for you, for the test, graph it in Desmos. Raise your hand, I can graph it in Desmos. Okay. Then go across, go find your y value. Okay, so like for instance 10 meters, you'd go over 10 meters till you got to here, which looks to be about a half a second, right? Is that the only answer? No, there's another one, right? Over here, there's another one, and that would be about 3.5 seconds, okay? So when it says that for part C, how would you do it? There is some algebra that will help solve that, but for right now, just use the graph. So part D, is it easier to compute the height given the time, or the time given the height? Here we go. Okay, so we're going to be given height. We're going to be given time. Find time, find height. You with me on what we're going to be doing here? Lauren, you can sit next to Maddie, okay? And then we're going to hear how the big party was at some point.
Sounds good.
All right. So this is the one that's easy. This is the one that's hard. Okay? Because if you're given a time, you just plug in on the other side. If you're given the height, like for instance, h of t is 10 meters. Okay? The only way that we know how to do that is to substitute in 10 equals negative 4.9 t squared plus 20t. Now there is one rule that helps us find that, and that is the zero rule of multiplication. Anybody know the zero rule of multiplication? If the answer in a multiplication problem is 0, if two numbers multiply equals 0, either A is 0 or B is 0. So in this case, we would just say 0 equals negative 4.9 t squared plus 20t. And then I'm going to put the 10 on the other side, so minus 10. Take out your graphing calculators. So I told you the only way you know how to do it is to use your the graph. But I'm going to show you on the graphing calculator how to do it. The first thing that you want to do, am I going too fast for you? The first thing that you want to do is to click Apps and find the app called PolySimul 2. If you do not have that app, raise your hand. Yeah, your calculator probably doesn't. I know it's not on the one that you can get on your phone. Because when I went to my graphing calculator on my phone and I pressed apps, the only one that was there was finance. So I don't know how you get it on the phone graphing calculator. I should see if I can find it. But anyway, if anybody not have it on their graphing calculator besides Dave? Okay, so I'm going to go to PolySimul 2, and then I'm going to press a key, Polynomial Root Finder. It's a second order, real number, decimal notation, normal, floating, radian, and then over here I'm going to click the button above next. Do you have it, Maddie? Okay, so do you know how to do this already? No.
No, but I have it.
Okay, so get to this page here. Yeah, go up one. Enter. There you go. And next. There you go. Okay, so it's negative 4.9. Enter. 20. Enter. And then negative 10. Enter. And then solve. And it tells me my two roots are at 3.49 and 0.58, which you saw on the graph here, right, when we had y equals 10, wherever we had it. Oh, that's not right. Okay. Number 3, the area of a circle. So notice I've got the formula for the area of a circle here, and I'm saying that the radius has to be greater than 0. Why is that? Here's a circle, it's getting smaller and smaller and smaller and smaller. Does everybody agree the smallest the radius can be is 0? After that, it would be a negative circle, which doesn't make any sense. So I'm starting at 0. And my formula says pi times the radius squared. So if you notice, I've got a curve going the other direction. Remember when we were dropping the ball, it was negative, and so the graph went this way. Now since it's positive, the graph is going to go up. Got it? Part A says, which is the dependent variable? Dependent variable is area. How do you know? It's outside the parentheses. It's on the left side of the equation. I don't know what other ways you would need to know. And then the independent variable? Radius. How do you know? It's inside parentheses. It's on the right side of the formula. I don't know what else there is to say. Here's the question, though. Yeah, we did this, right? For part, if the radius goes from 0 to 5, then the area goes from 0 to 78.5. Remember we did that yesterday? No, Maddie, you said that you didn't get chapter 2. Was that 2A or was that farther along? Yeah, we're not there yet, so don't worry about it yet, okay?
Okay, that makes sense.
Okay. So, for part C, what are the units that you would plug in for radius? 3C, what are the units? Yeah, it doesn't give us, no, it does say measured in inches out there for number 3. So the radius will be in inches, the area will be in inches squared, right? Everybody agree with that? So it's going to be in inches squared for part D. So we got the range in values to go from 0 to 78.5. Now remember how we got 78.5? Jess, what did we do? Don't remember. Somebody remember? Sam, what did we do? Put in 5 for the radius. 5 squared is 25. Multiply that by... They didn't say pi, they said multiply by, don't say pi, say 3.14. It didn't want us to give the exact value, it wanted to approximate to just one decimal place. So number 4, key concept. When representing a graph, one usually uses the horizontal axis for the independent variable. So in your graph, you would say independent and dependent. All right, so for the next one, let's look at it on the computer. So this is daylight in Boston. And as you go along through the year, there's more sun, less sun. And there's something spectacular happening Saturday night. Daylight savings time is ending, right? So we will get up. What's that?
Is it an hour of sleep?
It's an hour. And we lose an hour or we gain an hour of sleep. It's spring ahead, fall back, right? So when we get up at 7 o'clock, it will be light already because we're back to sun time. Okay? So this is the good time of year for people who like to sleep in. Right? Spring is the bad time for them. So, Janae, it's good this weekend.
Yeah. I was confused.
Yeah. Okay. So let's go through number 4. It says, what is the dependent variable in this case? Light. And how do you know? It's graphed on the vertical axis, right? And the independent variable? Day number. And how do you know it's graphed on the horizontal axis? You with me, Lauren? You got it? Jake, you good? Okay. Units on the independent or input variable. 15 what? 15 hours, right? Units on the independent variable, C, day number, right? The day number of the year. So E, what does -5 mean? Which would be about Christmas Day, somewhere around there, second Christmas Day. Could L of D ever be negative? The amount of daylight, can it ever be a negative number? It was so dark last night, there was negative daylight. If one were to plug in lots of values for D, what's the range?
Gosh, I hate that word.
So that is correct. Let's go through our notes. These are the choices for independent variable. They are called the domain. The choices for the dependent variable, these are called the range. Now, to help you remember which one is which, would you agree that X comes before Y in the alphabet? And domain comes before range alphabetically also. Okay, so that might help you remember that the range is the choices for Y. Don't be thinking about dependent and independent because those are screwed up alphabetically. So don't remember it that way. Page. To be or not to be? That is the question. Processes. So what they want you to think about in lesson 2B is the idea of input, okay, and output. So I'm going to put a number into the machine, and it's going to do a process on that number, and it's going to give me an output. So we go back here to these choices for representations of a function. Let's put them down in our notes. There are 4 function representations. First one is a equation. And they give us h of t equals negative 4.9 t squared plus 20t. The second one they give us is a graph. The third one they give us, that should not be in there. Is a table. Okay, and the fourth representation is words. And they say the height of the ball, t seconds, after it was hit. Those are the four representations. The test has a question on this one. And I'm okay with that because that is the hardest one for a function notation. But it's actually written the easiest way. The inputs are on the left side. So I'm going to put 0 into the machine. What is it going to give me out? I'm going to put 1 into the machine. Is it 1 or is it 0.5?
It's 1.
Okay. I'm going to put 1 into the machine. What do I get out? Okay. So it's written the most obvious way. But function notation acts the other way. We say height is a function of time. Right? Height is a function of time. That's what all of these are showing. What am I putting into my machine? And I'm getting out height. So when you see the words height is a function of time, the word before the word function is the dependent variable. The stuff after the word function is the independent variable. Page 20, 21, and 22 says on page 20, the table gives, this table below tells us about 4 different functions. Function lowercase t or f, function lowercase g, function uppercase a, and function uppercase t. It says for part A, match the description from the table to a representation that best matches the process. So here for number 2, here's the way I would do it. I would call F G, A, and T. And then next to it, I would write which of the 4 different representations on the next page talks about the radius of a car engine's piston and the temperature. So is that Roman numeral 1, Roman numeral 2, Roman numeral 3, or Roman numeral 4? I have to turn 4 sideways. Anybody have a guess as to which one it is?
Number 3.
He thinks it's number 3 because number 3 has degrees Fahrenheit and radius in inches. Why couldn't it be number 2? Because that talks about temperature and time. Why can't it be number 1? Because I don't see any temperature anyplace. I see area, right? Why couldn't it be number 4? Because we've got length and time. There's no temperature involved anyplace in there. Got it? So for letter F, I would write I. Okay? Then it says, label the representation using the appropriate function notation. So on number I, where we have that table, degrees and radius, I would label it, this is R is a function of D. I would write it that way for the label. Part C, is there any information that's missing from this one? It's got degrees Fahrenheit, it's got radius in inches, so this one is complete. Not all of them are going to have a part C. Under each representation, write a sentence that clearly indicates which quantity is a function of the other. So I would say for this one, radius. Why do I have D? Oh, degrees. Radius is a function of temperature. Got it? Do those other 3 just exactly like that. So you have to find G, work together as a team, get them done. Go.
I was looking sorry. Because I was like, the answer I gave you. 19. I don't even care if I get rid of something.
So, oh, do you mean like matching which one?
Yeah.
I think it's supposed to be both graphs.
Okay, so which one matched letter G? IB, good. And what was missing on that graph? I don't see anything missing because it's got time in seconds, it's got length in meters. And then how would you say it? Period of a pendulum is a function of its length. Capital letter A. Which one did you have for that one? I. And you would say area is a function of what'd you have? Radius. Is it missing anything? Maybe you should, I don't know, maybe you could put in inches or something. Like you could write area as a function of r. Area is in inches squared and radius is in inches. I don't know. T, what'd you have? Well, the only one that's left is double I, correct? Temperature, time. So we would say the temperature of an engine is a function of the time running. Why is it tough when you have temperature and time and writing function notation? Why is that a tough one? Yeah, they begin with the same letter. Here's the clues that they give you. Lowercase letter t is always a running time. Uppercase letter t could stand for temperature, but it could also stand for the period. As in, remember we were doing the length of the day in Boston? It could have been that, or the length of the time that it takes to go back and forth for a pendulum. Okay? Those would both be, they call them periods of the object, not the time of the object. Even though it measures time, it's not like 1 second, 2 seconds, 3 seconds, 4. It's like this is what happens as you go through each of those different things. Got it? C. Oh, did we finish that? I think we did. Okay, part C. Domain and range. As I said before, domain are the choices for x. Range are the choices for y. Consider the two functions p and s defined by the following formulas. P is 10 over the square root of g. That's saying the period of a pendulum is related to gravity. I'm going to show you something about that. Let's see here. YouTube. Chinese pendulum space. Okay, so this lady was up on a space station. Now, space stations have no gravity, not because they're so far away from the Earth, but because they're always falling. So she shows, I'm not going to turn up the song because she's speaking Chinese, so it doesn't. So what she does here is she lets go of the pendulum, and you can see what happens when she does. So she lets go of the pendulum, and it just stays there. So in that formula that you have on that page, period of a pendulum is 10 over the square root of g. Well, this is what happens on the Earth over on this side. Why? Because gravity is 9.8 meters per second squared. So you can see it's going to go back and forth. Why does her pendulum out in space not move?
Because the force of gravity isn't as strong.
Not only is it not as strong, it's not at all. So when you see period as a function of gravity is 10 over the square root of g, if this number here is 0 or weightless, the pendulum, the period, doesn't move. Have you ever heard this saying, you can't divide by 0? Now, the thing that I never liked about when the mathematicians would say, you can't divide by 0, I thought they were like scolding me. No, you can't divide by 0. That's not what they were saying. What they were saying was, if the denominator is 0, you've got big problems. And this is one of those cases. The pendulum will not go back and forth because the denominator is 0. So we would say in this case, g does not equal 0. Or we would say our domain has g not being 0. Do you know anything about the square root? Have you heard any stories about square root? What's that one, Felicia?
I don't know, you can't square root 0 or something like that.
You can't, well, you can square root 0. Press that on your calculator. So 0 square root does work.
Or is it you can't square root of 0?
Oops.
Or vice versa.
Just wait. So if I press square root of 0, my calculator says 0. So that's not the problem. Now say the other one that you were saying.
Or like you can't, like where the 2 is like the square, you put a 0, you can't do that.
That's true. You can't take the 0th root of a number, but there's something that you can't do with square roots. Very good. So let's try it and see. Like for instance, the square root of negative 16. My calculator says error, non-real answer. Now, it's not saying you can't do it. It's saying when you do it, you get a non-real answer. In this class, we don't do any non-real answers. There are some folks that get a degree from CVTC who do deal with non-real numbers. The electrical power distribution guys do because electricity, AC current, does have certain instances in which you get a non-real. What's the word that they use for non-real? Imaginary, where you do get imaginary numbers. So, On my calculator, it says in real mode, all calculations must result in a real number. So let's change our calculator to not real mode. So let's go to mode. Oops, I have to quit first. I'm going to go to mode and scroll down here to real. And I'm going to try this form right here. And second quit. Now when I do second function square root of negative 16, it says my answer is 4 imaginary. Okay? So the square root of negative 49, anybody know? 7 imaginary. Or the square root of negative 64? 8 imaginary. Everybody got it? We don't do any of that in this class. But what they want to show us here is that in this book, the domain won't have 0 or square roots as being possible. So, can we find S for any value of t? Sure. We just keep plugging in different values of t, squaring them. Are there any numbers that we can't square? Are there any numbers that we can't multiply that number by 16 and subtract it from 200? We will get negative numbers, correct? But we certainly aren't going to not be able to do it. I'll show you the graph here of this problem. So in this particular picture, I'm going to turn off that one. So in this particular picture, for every value of t, we can certainly find the height. It starts out here at 10 or 200 feet, and by 4 seconds, it's down to the ground. Now, if it's a rock, and you were over, I don't know, a hole that went down several miles, you could drop the rock from 200 feet. After a certain time, about 4 seconds, it will pass ground level, but then it'll keep on falling until it hits the bottom. Okay? So that one does work. Let's look at the second question there. Could you compute P of G for any value of G? Well, let's look at that one. If you notice here, we do have a problem. So I have to turn off the T here. We do have a problem. Because no matter how hard we try, this graph is not going to go into the negative category. We can't get a negative value on that graph. If I zoom out, no matter how far out I zoom, it doesn't go into the negative category. Page 23. It says, sometimes the context changes the domain and range of a function. So let's talk about domain. How old a person is. The domain. What are the choices for how old the person is? Nobody is going to be negative, correct? Nobody is going to be older than, I don't know, a couple hundred years. Even when you guys have grandkids, they probably aren't going to live to be a couple hundred years old. All of us are going to die at some point. Bad news? So, let's talk about the height of the rock after it's dropped 200 feet. Here's the picture. A, are there values of t that do not make sense in this situation? T is not going to be negative, correct? And it doesn't make any sense to say how far has the rock fallen 100 seconds later. Because where will the rock be 100 seconds later? On the ground, right? It falls to the ground. 200 seconds later, where is it going to be? On the ground. A day later, where is it going to be? On the ground. Okay? It's not. After a certain point, it's kind of dumb to keep track of where the rock is on the ground. B. What is the domain? So this is on page 24, B. Let's write it both ways. Goes from 0 to, on that picture, how high does it, or what's the biggest time that you're going to have? .5 something seconds, right? We could write it, time is between 0 and 3.5 something seconds. This is called interval notation, and this is called inequality notation. Okay, if that is true, what's the range? Oh, we should have said domain, and this is in seconds. What's the range? We would say from 0 to 200 feet. Now here's where people sometimes get mixed up. Where does it start? Where does the rock start? At 200 feet. So even though it starts at 200 feet, we give the interval, or we give the notation starting with the smallest value to the biggest value, right? Or we could say height is between 0 and 200. Okay? We're going to skip over number 3 about speed of light. So, we're going to build on that idea with the rock. 200 minus 16t squared. Where t is measured in seconds, s of t is measured in feet. So, s parenthesis 2, we don't want what it is, we want what does it mean. The height, when the ball has fallen for 2 seconds. S of 3, what does that mean? The height when the ball has fallen for 3 seconds. S of 2 plus 1. The height when the ball has fallen for 2 plus 1 seconds. Okay? Here's the question that we're going to be answering when we come back from the break. how would you interpret the following two quantities? S of t plus 1 and S of t plus 1. We'll see you after the break.
There's one that I got like 60. I don't think you get you. Oh. This is you're lucky. I love you. I love you. How is that true? Who told you it's cheating? You don't understand. This week's homework is literally item 2.
Really?
Yeah, it's like.
Is it to 4?
It's 2A. Oh, I did just for this week. I did 2A.
I just did from 1 to 4. Really? Dude, I've been freaking out about this and I just did
The other test is new.
like 1
Yeah.
people.
I don't know if
But I stopped. Sleeping.
we don't have This is make sure
No, yeah, I really like.
you didn't have class.
Okay, so
Or Wednesday.
I was like, I gotta do this.
Are you talking about this?
Oh yeah.
We're home in your car.
I didn't say it.
It's a solid movie. I don't know how much more I'm going to do. It's really sad.
Should do it? Okay, let's do it. Well, I've been I haven't. What's I don't know.
No, I'm really not. I don't like lately. I'm like just pretty much like, do I have free time? Very good. Okay, you're for sure coming.
Yeah.
So are you excited?
What?
Are you excited?
Yeah. Going to the next
Home decor. I don't know. I don't know. I have really pretty work in my life.
Oh, is it?
2 hours. I don't think they have that. I think it's really. Probably for sure. And then curtains.
Okay. So, use the formula for S of t given. Let's fill in the table here where we have t is 0, 0.5, 1, 1.5, and 2. So S of t, it tells us, is 200, 196, 184. Now remember, we're using the function S of t is 200 minus 16t squared. So how would we fill in this value here for 1.5? What would we press on our calculator? 200 minus 16 times 1.5 squared. And what does your calculator say?
164.
And then the last one, 200 minus 16 times 2 squared. What'd you get? 136. Now it says, instead of S of t, we're going to add 1 to t. Okay? So when we substitute in the first case, we get 184. In the second case, we get 164. What do you see happening in each case? It's the exact same answer as you would have gotten if you would have gotten it 1 second later. Or in other words, to find the answer, you just need to take 2 places down from where you are. So what would the next answer be after 164? Why can't we just copy down from the table for the one after that? Because it's not one of our choices, correct? So what are we going to have to do for 1.5? Well, we would not press 1.5 into our calculator. We would press 2.5, right? Because it's going to be our time plus another 1 second. So 200 minus 16 times 2.5 squared. And we get how much? $100. And for the last one, 200 minus 16 times what squared? 3 squared, and we get 56 feet. Next column over, S of t plus 1. So the first one they give us is 201. How is that 201 related to our first S of t? It's just one bigger than S of t. So do you think you're going to have to need your calculator to get to fill in the rest of this column? What are you going to do? Just add 1 to your outputs, right? What do you get for the second one down there? 197. 1, 1, and 137. So in this case, we shifted the output up 1. In this case, we shifted the input this case we changed time. In this case we changed height. Let's look at the graphs on page 28. Produce a graph for S of t on the first grid. This number, we don't have to go any higher than 200 feet. This will be 0 feet. This will be 0 seconds. If we go over here to 4 seconds, that's far enough. And we notice at 0 seconds, it's at 200. At 2 seconds, that'd be about right here, it's at 50, I forgot what it was, 56 feet? No, 136 feet, right? At 1 second, it was at 184. At a half a second, it was 196. So it looks kind of like that, right? If we connect the dots, we know that it's going to land here someplace out at about 3.5 seconds. If you look back, we had that graph recently, right here, right? Okay. B. Now we're going to produce a graph for S of t plus 1. So would you agree that at the beginning, it's the same spot that the other one was at 1 second? Correct? Look at the table. Let's make sure. At the beginning, it's the same place that the S of t was at 1 second. So here, it's also going to be shifted 1 second. Here, it's going to be shifted 1 second. And here, it's going to be shifted 1 second. Correct? Everybody agree? So the graph is going to go like this. Shift, input, 1 second back. So if we were going to really do this upright, when would the ball been at 200 feet? If we would have kept going back from 184, negative a half a second, it would have been at at 196. Negative 1 second, it would have been at 200. Everybody agree with that? So really, if we were going to play this game right, we would say that the graph, and you notice I dotted it because it doesn't really make sense. So here's basically what happens. Somebody dropped a rock, you open your eyes 1 second later, that's when time begins, and when time begins, that rock is at 184 feet. So it was so cute. We were at a birthday party and my granddaughter says, "Oh, I'm not going to let go of the helium-filled balloon." And I said, "Yes, you are, dear." "No, I'm really not. I'm never going to let go of it, Grandpa. I'm going to hold on to it forever." Okay? So then she reached for a can of soda, and as she reached for it, she let go of the string. Okay? And I tried grabbing for it. All right? Be the same thing as this case, right? You open your eyes and the rock is 16 feet down. You do not stand a chance. I was fishing with my brother-in-law one time, and he dropped his fishing rod over the side of the boat, and he grabbed it quick before it fell too far into the water. So I guess it is possible. But how far down is it at 1 second from where it was launched? What is that, about 16 feet? You aren't going to be able to recover that rock anymore. So our second picture will have, starting here at about 186, ending right around 2.5 seconds. Third picture. Now it says graph S of t plus 1. I'm going to do it on my same graph that I did before. And what's the difference? Well, at 0, I'm going to be 1 foot higher. At 1 second, I'm going to be 1 foot higher. At 1.5 seconds, at 2 seconds, 1 foot higher. So at 3.5 seconds, I'm going to still be a foot off the ground. So I'm shifting my output by 1 foot. In other words, when I let go of the rock, instead of letting it go from 200 feet, I let it go from 201. Okay? Here's the thing that people don't realize. This 1 is 1 second. This 1 is 1 foot. Okay? So they are the number 1, but if you get the units, you won't be confused. Now, which direction does an input shift change it? Left and right, correct? Mm-hmm. Which direction does an output shift change it? Up and down. So that S of t plus 1 and S of t plus 1 are two different things. Let's look at page 30. Our original equation was S of t is 200 minus 16 t squared. So I should have written it in, I'll change colors. So in our equation, wherever we see t, we are going to write something different. Well, we don't have to write anything different here because that's still 200. We don't have to write anything here because that's still minus 16. We're still going to be squaring. The difference is going to be What number are we going to square? T plus 1. Okay, now we've got algebra problems. When you multiply t plus 1 times t plus 1, you can, well, we better write down multiplication, because we might not be very good at remembering this. Some people use FOIL. Some people use the lattice. And some people use the tic-tac-toe. We are going to multiply t plus 1 squared, or in other words, t plus 1 times t plus 1. FOIL people, raise your hand. I FOIL it, a couple people. FOIL stands for first, outside, inside, last. What happens when you multiply the first two numbers together? You get t squared. Outside numbers together, you get 1t. Inside numbers together, you get 1t. And the last numbers together, 1 times 1 is 1. You can combine these two like terms and you get t squared plus 2t plus 1. I was never the lattice, so you guys have to help me with how you did this one. Does anybody use this one? I know what goes in each part. This is t squared, this is t, and this is 1, but I don't know how you get to that point. Here's the one that our book uses. We're going to multiply t plus 1 by t plus 1. T times t is t squared. T times 1 is 1t. T times 1 is 1t, and 1 times 1 is 1. And then when you add them together, you get t squared plus 2t plus 1. But remember, we have to multiply that by 16, so really we have 200 minus 16t squared plus 32t plus 16 which, if you notice, we will end up with s of t plus 1 is negative 16t squared plus minus 32t plus 184. Last one. Letter C, s of t plus 1, well, we just take s of t, 200 minus 16t squared, and I should have written a different color here, and add 1, and so combine these two together, you get 201 minus 16t squared. So, in this situation, for the first case, What can t go between from what number to what number? 0 to t, 0 to 3.5 or so, right around 3.5. In the second case, what can time go from? 0 to 2.5 seconds, right? Because it's going to hit the ground a second earlier than it would have before. Some people put down -1. I wouldn't object if you would, because really the rock fell 1 second before you opened your eyes. That'd be a way to think about it. And then for the last case, S of t plus 1, what happened? Well, it didn't change our time at all, right? Time still went from 0 to 3.5 seconds. Now, maybe it's going to hit a split instant later, right? But if a rock was going to fall on your head from 200 feet, it's going to hurt about the same as if it falls from 201, right? It's going to be pretty much the same thing. Page 31.
So when do we write the last one then? Or is number 7?
I would write from 0 to 3.5, ... because it's not exactly 3.5 seconds. It's a little bit more than 3.5 seconds. From the early 1980s through 2000, states kept record of the number of bald eagle breeding pairs. Why do you think they wanted to keep track of the bald eagle breeding pairs? What?
Because they were super endangered.
They were super endangered, okay? And we're talking about linear population growth. So the population of what is going to be growing in this case? Eagles. Very good. So let's look at the graph on the next page. 1803, 2463, 3123. Would you agree the number of eagle pairs is growing? How do they show that on the bar graph? The bars are getting bigger, right? In the next case, T is the number of years after 1986. So if T is 0, there were 1,803 breeding pairs, population as a function of time. So at 2, what number should we put in? At 4, what number should we put in?
31, 23.
Fill in the rest of the table. So 6, 37, 83. 8, 44, 43, 10, 5103, 12, 5763, and 14 was 6423. Okay, so we've got our table filled out. Number 3 says, does it appear they are growing linearly, like a line? If you look at the graph, what do you notice about the graph? If you put your pencil on your paper, right? It looks like you can cover the points with a line, right? Number 4, find the growth rate. First of all, we've got the idea of a rate. What does a rate mean? If you say something is a rate, like you get paid $12 per hour, or you're driving 55 miles per hour. What does rate always mean? We're giving a fraction, correct? So on our table, we're going to find a fraction that is the growth rate, and we're just going to call it m. What's growing? And what's it growing compared to? Okay? So we're going to do the change in population divided by the change in time. That triangle is the Greek letter delta. The change in population. In the first case, here's how we're going to do it. We're going to take the second population minus the first population. Or in other words, 2463 minus 1803. And we're going to compare it to the second time minus the first time. Well, the second time is year 2, and the first time is year 0. So on our calculator, we're going to do 2463 minus 1803, and we get 660 for every 2 years. In the second case, what numbers are we going to press? 3123 minus 2463, and we get, actually I should have put this one into this spot here, shouldn't I? 660 in 2 years. How about the next one down? 3783 minus 3123. Anybody take a guess? 660 in 2 years. Do you see a pattern developing here? So what's the next one? 660 in 2 years. 660 in 2 years. 660 in 2 years. Let's do the last one just to make sure. 6423 minus 5763 is 660 in 2 years. Now there might be an advantage to not write at 660 in 2 years. There might be an advantage in saying 330 per 1 year. Okay, that might be advantageous. Because if they asked us to find out how many there were in 15 years, that's not one of our choices. But we could figure it out, couldn't we? So, if the ROC, which stands for rate of change, is constant, the function is linear. Now, one of the things that I'd like you to notice is why did we take the second one minus the first one? If we would have taken the first one minus the second one, our denominator would have been a negative number. We don't like negative numbers. We want our numbers to always be, our denominators to always be positive. So always take the second one minus the first one. Number 5 says, find a formula for P of T. This number at the end is the beginning value. What is the value? How many eagle pairs were there at the beginning? 1,803. How many pairs did it increase each year? 330. So this is the letter M for slope or rate of change, and the B just stands for beginning value. So we should be able to figure out how many breeding pairs there are at any time, because all we'll do is multiply the number of years by 330 and then add 1803. So let's look at the problem here. In 2006, the year before bald eagles were removed from the endangered species list, the number of breeding pairs was 9,789. What would have our prediction been using our formula? Population. What number would we substitute it in for the time instead of 2006? Where'd you get the 20 from?
2006 is 20 years after.
2006 is 20 after 1986. So what are we going to do? We're going to take 330 times 20 and add 1803. And we get 8403. So if we follow our linear model, after 20 years, we expect to have 8,403 eagle pairs. How many did we actually have? 9,700. What did it say? 89. So at some point, this quit being linear and started being exponential. Very good. And I think it's crucial in that understanding to look at the actual numbers. This graph was adapted from the actual population data. They made it be 330 eagle pairs per year. The actual numbers, I think I've got them here. The actual number of eagle pairs, let's see here. This is from the Fish and Wildlife Survey. This is the actual numbers that there were. And what's interesting about it is that they used the exact same graph, because if you notice in 2006, They have 9789. But 1986, what did we have as our number? 1803, and there were actually 1875. So you see how they tried to make it be linear. They took the actual data and they made it so it was linear just by every 2 years adding 660 eagles. Okay? Do you notice what's happening here about 1996, actually closer to about 2000? It starts swooping up. The states kept track of the eagle breeding pairs from 1986 to 2000. Why did they stop in 2000? Because they weren't worried about running out of eagles anymore. They were starting to increase exponentially after that point, and so they said, we don't have to worry about them anymore. They took them off the endangered species list. Why? Because they weren't linear anymore. They were starting to gain traction. And so now, raise your hand if you've seen a bald eagle. Okay? When I was a kid, there may have been one person that would have raised their hand that they had seen a bald eagle. We just didn't see them. Were there bald eagles? Of course. We just didn't see them. Page 23. Now we are going to talk about rabbits and foxes. So here's a graph that shows rabbits and foxes, and I need you to make a modification on your graph because they took off the representations. So they're showing rabbit population and fox population. Based on that graph, the number of foxes is increasing over time, right? Based on that graph, the number of rabbits is decreasing over time, right? So when we were talking about population growth, if this number is positive, the line is sloping up. So let's look at our graph of rabbits and foxes. This is decreasing. Its sign will be negative. This is increasing. Its sign will be positive. How many rabbits were there at t equals 0? What is the rate of change of the rabbit population? For every year you go over, here is the answer for number 7b. All parts of that are necessary. You can't just have 10, because 10 would be the wrong answer. On the test, you will write 10, and I will mark it wrong. In intermediate algebra, I did not mark it wrong. But this time, dang it, you need to get the signs right. Okay? No more mamby-pamby, 10, negative 10, it's all the same. No, you're in college algebra now. Okay? Negative 10. Now, you could say 10 rabbits per year decrease. I would accept that. Okay? The other part that you need to have is you need to say rabbits per year, because the unit is crucial. Got it? C. Is the number of rabbits increasing or decreasing? Decreasing. How do you know? There's 3 ways you know. First of all, the sign of our rate of change is negative. The line is sloping. I guess there's only two ways. The line is sloping down. Number 8, the two graphs cross when t equals 4. What does it mean?
There's the same amount of foxes
When?
in 4 years after 2000.
Okay. And can you tell me anything about how many of them there are at that time?
40.
40 rabbits, 40 foxes after year 4. Now, this is kind of a goofy graph because, well, for one thing, foxes don't only eat rabbits. But the other thing is, if a fox was only going to eat one rabbit per year, you can see that would be problematic, right? Okay. Well, we had a rabbit back in March 13th, if I remember. Yep, it was March 13th. We are not going to have another rabbit until next March 13th. You're just going to have to go hungry, right? Obviously, there's some other numbers that go into this. So, let's look at number 9. A. R of 2 minus F of 2 means the change or the difference between the rabbit and fox population in, I forgot what year it was. (2007). What was the answer? Well, how many rabbits were there in year 2?
60.
How many foxes were there in year 2? So we would say the difference right here is 30. Okay? B. R6 plus F6 is the total number of rabbits and foxes in (2011). How many was it? If we add those two numbers together. Well, rabbits in year 6 is 20. Foxes in year 6 is 50. So the total was 70. Part C, F of 4 minus F of 2. You're going to need to know this one for the test. Whenever you see the numbers being subtracted this way, where you take the bigger one minus the smaller one, you always can write change. So the change in fox population between 2007 and 2009. Notice I wrote 2007 first because that's the number that we're subtracting. I wrote 2009 last because that's the number we're subtracting from. What is the change in fox population between those 2 years? Year 4 and year 6. How much did it increase? $50 minus 40 is 10, correct? Part D is the rate of change formula. It's the slope, M, which is the change in Y over the change in X, or in our case, the change in F of over the change in X. And it's going to be the second one, F of 4 minus F of 2 divided by, notice it's rate, which means it's going to be a divide by 4 minus 2. Notice these two numbers match. Four minus 2 is 2, correct? How many foxes were there in year 4? Oh, we just did that one, right? 50. How many foxes were there in year 2? 40. So we get 10 divided by 2. I'm getting more and more comfortable with saying 10 for every 2. But mathematically, what would they tell us to do? Change that to 5 foxes per year increase, right? It's an increase of 5 foxes per year. At what point does the model become unrealistic?
After 8 years.
Yeah, we ran out of rabbits. So the foxes are going to die off after that time. Hey, so there's a similar operation going on Isle Royal up in the, yeah.
I just had a quick question on like the change part. So part A and B were different, but part C was changed.
Part C is not, yes, it is. You know what? You can see why A is, even though it's a subtract, why it's not a change, right?
Yeah.
Because it's not the same variable. Whereas in C, it is a change because we're talking about the same variable and we're listing them in the order of the second one to the first one. D is a rate of change. Whenever you see a fraction, remember the word rate. It's the rate of change. Okay, so anyway, Isle Royal up in Lake Superior, they just are doing something to control the growth of the moose population. Moose population and skyrocketing. What are they doing? Nobody knows.
Limiting tags.
There's no hunting allowed on Isle Royal. There's like 1,800 moose. They just put a whole bunch more wolves onto Isle Royal. They used to have a number of wolves and a number of moose, but then the wolves just started interbreeding, and they ended up with a grandma wolf and her grandson were the only 2 wolves left on the island. And because she was the grandma, she couldn't have pups anymore, and so it was not going to work. So then they're going to haul in like 25 more wolves onto the island. So the wolf population will increase, and the moose population will decrease. That's what they hope. We'll see. Page 3B. Anybody ever had a moose? Nobody. I have to take attendance here quick. Ugh, so frustrating. Okay, Nick. Mike.
Yep.
Marlena.
Yep.
Gavin. Janae. Felicia. Nicole. Eric.
Here.
Phil.
Yeah.
Grant. I knew somebody wasn't going to be here today. I couldn't remember. Connor. Paige. Eric. Laura. Madeline. Sarah. Bailey. Jess. Lauren. Jake. Chris. And Sam. Okay. So I'm going to get started here at least with President Obama's speech on page 37, and I think that's all the farther we'll be able to get. To check here.
Good afternoon, everybody. Please be seated. Incentive to help distribute personnel and aid on the ground. We are going to create a new training site to train thousands of health workers so they can effectively bring more nations together to strengthen our global health security so that we can better prevent, detect, and respond to future outbreaks before they become epidemics. This is actually something that we had announced with force and make sure with 4 goals in mind.
Here we go.
In the hardest hit countries, Liberia, Sierra Leone,
Whoa, that's loud.
and others recently returned from the region, and the scenes that they describe are just horrific. More than 2,400 men, women, and children are known to have died, and we strongly suspect that the actual death toll is higher than that. Hospitals, clinics, and the few treatment centers that do exist have been completely overwhelmed. An already very weak public health system is near collapse in these countries. Patients are being turned away, and people are literally dying in the streets. Now, here's the hard truth. In West Africa, Ebola is now an epidemic.
This is the quote.
That we have not seen before. It's spiraling out of control. It is getting worse. It's spreading faster and exponentially. Today, thousands of people in West Africa are infected. That number could rapidly reach tens of thousands. If the outbreak is not stopped now, we could be looking at hundreds of thousands of people infected, with profound political and economic and security implications for all of us.
So my question to you is this. This says models of exponential growth and decay. Do you think in this case, when we talk about Ebola, that we are going to have a linear function? No. We're going to see what exponential is next time here in college algebra.
See that? The entire next lesson I did.
Do you think, Madeline, you'll be able to get those now? Give it a shot.
We
And
had
then,
part C in the homework. And part C's not in the book. And part C has to do with all the range stuff, and I had no idea.
no, but now do you think you'll be able to do it?
I don't know.
Okay, well, give it a shot and let me know. Yes. Thank you very much. Appreciate it.
But a lot of what
was
I
a good
did,
way to start.
I got wrong
I mean,
because I didn't
I'll
know
be
if it was
honest,
doing
I
it right or
discovered
not.
it
So I don't know if I can do it.
Oh, yeah, you totally can redo it. Yeah, yeah. And you should be able to go in and do those.
And then
what everything should be like.
Is that, we have like an assignment that's on a Sunday.
I just changed the due date last night because I got home.
Okay.
So you can go in